Do you know we are entering a new space age? This new era, the 21st century space age, will be a highly commercialized sector with critical roles played by industry and space agencies alike. To give you a sense of the exponential growth we are anticipating, let's look at these numbers. From 8,000 satellites that we currently have up in space orbiting us, since our forays into space began in the 20th century, we will be launching 100,000 satellites in the next decade. But that's just one facet of what's to come. In fact, in this new age, we will be launching way beyond the near-Earth orbits. We will be going much farther. Under the Artemis program, NASA plans to establish the Lunar Gateway, a space station in the lunar environment that will enable human presence on the Moon, Mars, and beyond. Make no mistake, though, space is a highly challenging environment with wild temperature swings, vacuum, and damaging radiation, including protons and electrons coming from the sun. So space electronics needs to be tolerant to all these stressors and challenging environments. Now, back in the 20th century, the primary goal was to launch satellites into the low Earth orbit, or LEO, roughly 400 kilometers from the surface of the Earth, for applications ranging from weather forecasting to telecommunications. This was enabled by a material called silicon, a fairly space-reliant and space-resilient semiconductor. Silicon solar cells powered those satellites. Now, in this new age, the new and upcoming space age, we will be having our presence and establishments beyond Earth. Additionally, the low Earth orbit is fast getting crowded, and so we need to launch higher anyway. This will expose space electronics to even harsher, even more challenging conditions. It's clear we would need a new space technology to sustain this impending revolution. This technology needs to be more resilient than silicon. Today, I'll tell you about a future semiconductor technology that can potentially enable the new space age. My research over the past 10 years has explored semiconductor inks that can be printed into thin-film electronics using low-cost newspaper-style printing tools, very similar to the Kodak printing process, the legacy of Rochester. However, it was around 3 years ago that I started researching a next-generation semiconductor called metal halide perovskite for space applications. This was around the start of 2021 at the peak of COVID. I was a researcher at the National Renewable Energy Laboratory, NREL, in Colorado, and was collaborating with NASA. The sheer ease of manufacturing perovskites, their low cost, and their lightweight are all key attributes that can vastly benefit the new space age. However, research at that time was pointing toward surprising radiation tolerance of perovskites. Now, let me explain this surprise to you. Perovskites are a very brittle and unstable material when exposed to moisture and oxygen. So much that if you were to take a perovskite film out on a rainy day, it's going to fall apart. It's going to be brittle and destabilize fairly quickly. And that's because perovskite wants to dissolve in water, just like salt in water. Space environment does not have moisture and oxygen, obviously. So that's not a concern, but that's sufficient to tell you that perovskites are very brittle and unstable. Now imagine taking this perovskite film and shooting space radiation on it. It'll then be very bizarre if this film is to withstand radiation levels almost 100 times more than what silicon can withstand. Wouldn't it be surprising? Yet I and others have repeatedly observed this over the past few years. Now, in a paper I published earlier this January, we have tried to shed some light on this mystery. We found that perovskites, what you see on the left-hand side, can be degraded by space radiation, sure, but space radiation also heals them. It's as if damage and healing are going on at the same time. It's as if perovskites are a soft, reconfigurable material. In fact, we found that radiation would knock atoms off of these crystals in the perovskite, leading to a drop in performance of the solar cells, only for those atoms to come back to their original positions after a while, leading to recovery of the solar cell performance. We believe this happens because perovskites are intrinsically soft crystals, thanks to their vibrational modes. This is very unlike conventional semiconductors, like silicon, which are rigid crystals. This lattice softness opens a whole paradigm for extreme tolerant materials. Self-healing materials can operate for significantly longer times in space, potentially, compared to conventional semiconductors. Add to this the fact that perovskites can be manufactured at low cost with ease. It might be possible, actually, to manufacture perovskite electronics outside of Earth, directly on Moon and Mars, and this would significantly cut down launch costs and payload weights. My research at RIT explores perovskites for space. Being at the cutting edge of this emerging field, I can see Rochester has a lot to offer. This was the birthplace of Kodak that taught the world how to print semiconductors at scale and at speed. Listen, this new space age will be a vast market with endless opportunities. A huge workforce will be required. This will be a great opportunity for students to join the tide and enable the future. Together, we can launch higher, launch more, and play a role in defining humanity beyond Earth, one perovskite-powered satellite at a time. Thank you.